Mike asked me to come today and talk about some of the guts of Realm's deferred allocation stuff. Since I'm in presentation mode, I can't actually see people's faces or hands or anything, so just interrupt me as you have questions. I have a bunch of slides I want to go through first because I think the code itself is actually pretty opaque if you just jump right into it. So I want to explain kind of what we're doing and why the code should be the obvious spaghetti that would be necessary to pull off the things that I'm going to describe here. So I'll go through the slides and then, like I said, interrupt me as you like. Starting with some motivation, what is deferred allocation in Realm and why are we doing it? And so hopefully a bunch of this is not new to folks, but to remind you what points are relevant. Realm is about, one of the key ideas in Realm is hiding latency, and the way you do this is you want to overlap computations and communications with other stuff. And the way you find things to overlap is you let the application's control plane basically run ahead of the data plane. So the thing that's saying what I want to do runs far ahead of what's actually currently being done at the time, which is how Realm can see, that an application wants to do two independent things. We don't ask the application to take those two things and interleave their enumerations tightly in the code. We let the application kind of describe all of one thing it wants to do and then come back and describe all of something else it wants to do. And we rely on the ability to get all the way through the first thing in the control plane without stopping the application so that it can get on and start telling us what the second thing it wants to do is. And so we need to, so if you think of a control data plane, we need to be able to keep the control plane running ahead of the data plane and not slow it down if we don't have to. The next kind of fundamental idea is that dynamic allocation is essential to any workloads. Hopefully I don't have to motivate that one too much. But the place these two things run together is that if you provide an allocation interface for memory that is blocking, you basically have to choose between one of two evils. I talked about one of them here, which is that, the first one, which I didn't talk about, is if you stall the control plane when it wants to do an allocation, then we're clearly not satisfying the first bullet. But if you've got a blocking interface and you don't want to stall things too early, then basically you just need to, effectively what you're doing is just increasing allocation lifetimes. Right now, an allocation has to live from the first time it's mentioned in the control plane to the last time it's used in the data plane. And this increased lifetime means that you have a larger working set. And if you have workloads that tend to be memory capacity limited, which are pretty common, then now you've got a straight up trade-off between what size problem you can handle and whether you're going to be able to expose the asynchrony that we need to hide latency. I kind of described it as a negative. We need a non-blocking allocator that allows us to keep our allocation lifetimes precise. And still allow the control plane to run ahead. There's a second piece, though, to the observation that many workloads are memory capacity limited, which is that if we have applications that are used to trying to use all the memory capacity that they have, they need to get good feedback at when they're at the limits of the capacity, right? If we let things just silently oversubscribe the memory system and either thrash or out of memory fault, that's not a very great experience. So even though we want to provide a non-blocking allocator, we do still need to give feedback when capacity limits are reached. Basically, we want to be able to have malloc fail, say no, you can't allocate anything new because you're out of memory or you would be out of memory, so that whatever's sitting on top of Realm, say Legion and an application mapper, can decide to do an alternative mapping decision, right? They can choose, do I either wait and accept that things are not going to pipeline as much as I'd like, or do I choose to allocate somewhere else? And that's feedback that's a decision you can only make if you're told, hey, there isn't room for what you want to do at the time you want to do it. So based on that, there's two goals of the deferred allocation stuff in Realm. The first one is that we want to permit allocations that are not possible at this instant, but will be possible eventually. And so since the control plane is operating ahead of the data plane, what you really want to be talking about is allocations that will be possible at that spot in the future where you're going to get to the stuff that you're talking about, the tasks and the copies that you're describing now, which is not what's executing now. So we need to do that. But on the flip side, we also still want to be able to reject allocations that would take an application take its working set beyond the available resources. So we're trying to kind of provide a kind of decouple it in time, in the sense that we want to be able to talk about the state of the heap in the future, not the state of the heap at the moment, without accidentally making that heap appear to be infinite in size. So any questions about this? I feel like I didn't do it quite the justice that I wanted to, but right. So the goal here is we want something that understand that there's a finite amount of memory and that we want to not oversubscribe it. But we also need to be thinking in the future rather than the present. And just because something isn't available now, if it's going to be available future, because we've already scheduled the deletion of something that's currently in memory, then we want to be able to allocate on the basis of that deletion happening sometime in the future.
I assume goal number 2 is the hard requirement and goal number 1 is the soft requirement, right?
Yes. Yeah, basically, it is possible for the deferred allocator to claim it's going to allocate something and then come back later and say, just kidding, I couldn't. But that's restricted to only cases that'll get to the end where something else went wrong also, and that's fallout from it. But yeah, the idea is, in the absence of any unexpected termination of things, then we never want to say that we can allocate something that can't actually work. So we never want to hang, we never want to out of memory, we never want to thrash.
Can you maybe you want to save this to the end, but can you contrast it with CUDA memcopy async, or sorry, CUDA malloc async?
I can try. Let me give the short answer now, and then.
Yeah, if you want to save the longer answer for the end, that's fine.
Let me save it, because I'm sure it's going to involve folks like Corey correcting me on my exact understanding of CUDA. No. Yeah, there are some important differences, so yeah, let's try to make sure we cover that before the end of the hour.
Yeah, that's fine. You can do it at the end.
This sounds similar to lazy evaluation and thongs in Haskell. Was that a source of inspiration, or is any similarity behind the curtains?
Well, you'll see it's very not lazy, and I think it needs to be not lazy because of this goal number 2. Right? Basically, we need to eagerly detect cases where we would run out of resources in the future. And what that really means is we're going to eagerly plan for the future and actually have a picture of what the future looks like now, rather than putting it off to later.
Okay. Thank you.
Sure. Okay. So let's talk about some limitations. In order to solve these things, we have to accept some limitations. So the first one is that not all realm memories actually support deferred allocation. Pragmatically, if you look in the type system, it's only those that inherit from local managed memory. But the real reason for limitation has to do with what the underlying allocator is. And because of this wanting to basically maintain both a present and a future setting, it turns out you need an allocator, basically a heap manager, that's separate from the actual resource being managed. So you can't implement this as linked list chained through the same memory that you are managing, for example. A state that's clonable and copyable. Basically, we're going to be creating and destroying, either real or possible future states of the heap at various times. Very, very importantly, it needs to be completely deterministic in its allocation decisions, right? If I start from initial state and do X, Y, and Z now, then in the future, if I had that same state and I do X, Y, and Z, I need to know the outcome is going to be identical. We also need to be able to test if an allocation will be possible without performing it. And then the fifth requirement here is that because we are going to be maintaining multiple heap states, we need an allocator that's relatively efficient, relatively low cost in performing allocations and deallocations. So there is a trade-off here. The most heroic allocator that gives you the best possible defragmentation utilization might actually be too expensive to run 4 or 5 copies of, or well, 3 or 4 copies of. So there's a trade-off to be considered there. And then, in addition to the allocator itself, the deferred allocation stuff itself has to be somewhat conservative in decisions about resource exhaustion. And this gets to the point that I think Manolis was getting to before, that being perfect about making the maximum possible use of resources in the future requires, trying to decide, I think it's exponential complexity in the number of pending allocations. And that's much too expensive. And so the allowing something that will be able to allocate in the future is very much a best effort thing. It turns out best effort is good in a lot of cases, but it's easy to come up with cases where it seems like an allocation should be allowed and isn't, because the algorithm is not able to try all the possible permutations that would lead to finding the right one. So any questions on this? The kind of the reason I wanted to highlight the idea of what the underlying allocator is, and I'm now going to talk briefly about what the actual underlying allocator is today. But importantly, there's a separation here that we can improve that underlying allocator to some extent without messing up the deferred allocation logic that sits on top of it, and that was part of the plan. Okay, so the basic allocator that the local managed memory sits on top of is called the basic range allocator. This is a templated type. It's in dem-impl.inl. I should have had a list of the file names, but I'll walk through some of the files in a few minutes. But basically, it's a range-based allocator, so it keeps track of ranges. It's templated on what type you use to describe the start and end of ranges. So like size T is a good choice, but also what is the tag type? What is the label you associate with each range? And since we're allocating instances here, then what we're going to associate is a realm region instance handle ID with each range. This thing is currently a simple first fit allocator. And basically just keeps track of, breaks the overall thing into a bunch of ranges, and the range is either allocated and associated with a given tag, or it's free. And we have 2 doubly linked lists, one over all the ranges and one over the free ranges, which makes it straightforward to do a first fit check. You can just iterate over the free ranges and grab the first one that's big enough, and break off the remaining free subset subrange if you don't need all of it. But also, if you delete a range, if you free an allocation, then the double linked list over all ranges makes it easy to find the one before you and after you, and see if you can merge with other free ranges, or if you need to create a new free range. Not super exciting, but as I said, the point of this structure is that if we wanted to improve this, there's a bunch of room to improve it without having to go question whether it messed up the deferred allocation stuff. With Realm, we do have to talk about thread safety a lot, and so in particular, this allocator is not intended to be thread safe. It assumes mutual exclusion is enforced at the higher level, basically at the local managed memory level. So we don't have to worry about hardening each of these data structures. And as you'll see, since we often manipulate multiple of these allocators in certain cases, atomicity on a single allocator wouldn't even be strong enough anyway. Any quick questions? I will show the code for this in a bit, but I want to get through what I'm describing before I actually point out the code.
Yeah, was that inspired by Andrei Alexandrescu's small allocator example in his book? Because it looks a bit similar with the double.
Yeah, I mean, not directly. I think I probably have looked at that book, but I didn't crib from it. But yeah, the idea that you keep track of ranges and master state is pretty common. If you're doing a first fit allocator, then it's great. If I wanted a best fit allocator or something that was smart enough to think about defragmentation, I would probably need a richer data structure. This was just a quick and dirty thing. It, honestly was meant to come back and make it a little smarter, but that was 5-6 years ago, and I hadn't gotten around to it yet. So if somebody else gets to it, I certainly won't complain. But it's instance allocation is not is not quite as performance critical as as tasks and events and stuff. So it just hasn't poked up as the tall nail yet.
Yeah. Thank you.
Sure. Okay, my next slide, I want to talk a little bit about, since I'm making this distinction about the separation from kind of the control plane and the data plane, I want to talk about what is the instance lifecycle from the control plane's view, because it's not quite linear. From the data plane's perspective, life is simple. There's a point at which the instance is allocated and ready to use, and there's a point where it goes away again, and that's a nice, single range. Allocation is trickier because of a number of steps. So let me kind of walk through it. It ends up being sort of diamond shaped. But if we look at the side on the left, the column on the left here is the way allocation is done. So the first step is that the control plane will ask that an instance be created. And among other things, the control plane will supply layout information, which implicitly describes what is the size of the allocation that's needed. And it will also give a precondition event that should be satisfied before the instance is created. And now, if there is a precondition on the allocation, we basically, we do one thing right away, which is as soon as we're given the layout information and the precondition, then before even consulting the heap state or anything, we immediately hand back an instance ID and an event that will speak to when the instance has actually been created. So this happens instantaneously, even if the precondition isn't satisfied. So this allows this interface here, this create instance call, to return immediately to the caller, even if we've actually done none of the allocation work yet. This does mean, interestingly, that although I said the actual memory occupied by the instance, we don't want its lifetime to be extended to cover the control plane, it is true the instance ID. The instance ID does live for from the point at which the control plane starts wanting to talk about instance until when the data is actually the instance is actually freed in memory, which is hopefully sometime after its last use. I haven't seen any cases yet where the increased lifetime of instance IDs is a problem, but if it is a problem, it's an easier problem to fix than not having enough memory to actually cover the real allocations. In any case, once we do this, basically nothing else happens inside of Realm until this precondition is actually satisfied. And once the precondition is satisfied, then we call into a method, which I'll show you all in a moment, called attempt deferrable allocation. Right, and so this is the thing that's now actually going to say, okay, now that I know it's actually time to do this allocation, or time to potentially do it. I'm now interested in this allocation happening. Let's see if we can actually do it. And so this is going to consult the state of the allocator in ways I'll describe in a moment, but it's going to return one of three answers. It's either going to return an answer saying, yes, I'm succeeding immediately. And so I'm going to hand you an instance alloc result profiling response that says, yes, it's allocated. And I'm going to trigger this eCreated event and say that it's done successfully. The other instantaneous response can be that it can be failure. It can be no, there's just no room for this, and there won't be. There doesn't appear to be any room for it in the future either. So we'll fail it right away. And again, we'll return that with a profiling result. And in this case, the eCreated event will be poisoned. So that anything that was downstream of it will know, okay, this allocation is never going to succeed. But the third outcome is that we can't make an instantaneous call. It looks like there will be room in the future. And so I'll show you how that goes into data structure. And so we return an instance alloc result saying we think it's going to work, but we don't trigger the event yet because we haven't actually allocated it. And we won't actually allocate it until some other instance is released, right? If we're going down this path, it's because there wasn't room now, but we think there's room in the future. And so when that future becomes the now, at that point, can say, okay, yes, this instance has been created, and return trigger this eCreated event and therefore enable whatever was downstream of that event in the operation graph. So that's the allocation side of things. There's also the deletion side of things, and this is a little bit simpler, which is that at some point the control plane will say, I would like to destroy this instance, and that calls region instance destroy, but it follows pretty much straight through into local managed memory release storage deferrable. Okay, and it does that even if the precondition isn't satisfied, and I have a typo here. This is the key of deferred allocation, which is that as soon as the control plane tells Realm that a deletion is going to happen and gives it a concrete precondition, then Realm now knows there's a future where that's going to go away, and that will be the thing that enables it to do deferred allocation. But it also means the release is done in 2 steps. The deferrable says we're going to do it, so we track it, and then at some point later when it actually happens, that's when we know that it did finally happen. And this is where the other profiling results that sometimes use instance status or instance abnormal status would come back, because this is when the lifetime, actually instance timeline also would be returned here. So we have the allocation kind of flow and the deallocation flow, and they're able to overlap some. And that's why I drew these 2 red arrows in. One overlap is sort of convenient, one constraint is sort of convenient required by the current implementation, which is that Realm doesn't want the control plane to destroy an instance until it's at least attempted the deferrable allocation. That's just a limitation of the current code. If there was actually, if Mike actually needed to do this in Legion, then this would be relaxed, and we would basically just remember, we would assume that a deletion for an event that we haven't done this for is just remembered and done later. But then this arrow here is much, is more real, which is that you can't actually destroy the instance until you're done using it, which better not be before it was actually created. And so if this ordering isn't satisfied, then Realm will get pretty unhappy. There's no, Realm doesn't automatically enforce this. It's just that if you destroy an instance with a precondition that is not somehow a consequent of the created condition, then you're very likely to have Realm barf on you because it thinks the actual instance timeline is inside out.
And we have observed that. We have observed that in practice. I actually have the check in Legion to actually make sure that we don't try to destroy the instance until it's actually been created first.
This created or this created? I mean, you're allowed to request deletion as soon as you've got an instance alloc result.
Right. Yeah, the second one,
okay.
I think. Yeah.
Okay. Well, I'll say if that's horribly inconvenient for you.
It's not inconvenient. I'm just saying we have tripped over it. It's not. You're not theorizing.
Okay. It would not be horrible to deal with, but if I don't have to, that's even easier. Okay, so that's that timeline. The next picture I have for you is kind of what the deferred allocator looks like inside.
Can I ask a quick question about the Legion side of things in the previous slide?
Sure.
Mike, is it correct that in Legion, if I'm in a mapper and I'm trying to create an instance, like a Legion instance, then ePre will be no? Is that right?
So we do the instance call, and then like if you're in Legion trying to create an instance, like we will call create instance, right, and we get back the event saying when we'll get back the ID, right, and the e created, right, and then what we do is we actually will block waiting for that instance alloc result profiling response to come back to us, because like we can't safely tell the mapper, whether the instance has been allocated or not until we actually get that response. And so and we need to tell the mapper one way or another. The mapper is not. I decided not to expose this level of detail to the mapper where like it would have to deal with the profiling responses for instance allocs and stuff like that. It just felt a little too complicated for the mapper interface. And so we actually will block waiting on that instance alloc result and then check whether Realm has said the instance allocation is going to succeed or not, and then respond back to the mapper.
That's right. Yeah, but because your interface with the mapper is actually a blocking one.
Yeah.
To Manolis's question, means you don't actually use the precondition on creation. You never want to talk about an instance that's being. Yeah. It shouldn't be considered until the future. You want it to be considered right now so that you can get this instance alloc result information back to the mapper.
That's right. Yeah.
And actually, I don't have a slide for it. It turns out that.
Well, I do have ePres sometimes. In particular with garbage collection, because sometimes like the effects of garbage collection, I want them to ripple through the machine, and there might be some some pending work to happen there. So sometimes there is an ePre.
Because you want it to be considered after the garbage allocation.
Exactly. I don't want the allocation. Exactly. I don't want Realm to try to do the instance creation until I know that the effects of the garbage collection have rippled and all the destroy calls have actually been done.
Okay.
So,
Well, that was exactly the example I was going to give for why you would use it. So,
Yep.
So you are using. Excellent. Okay. Then what I will say is, as I was thinking through, I didn't get a chance to put in the slides. I think there actually may be one bug related to that that can cause an event loop, and I will chat with you offline about it. It may in fact be one we bumped into and you've already worked around.
Okay.
But and it's also related to the idea of we were talking ballistic events last week. Basically, there's a problem where an instance that is created with a precondition doesn't actually necessarily get put in the right spot in the overall ordering when replays need to happen.
Okay.
So we need to think through that, but I won't try to do it on the fly here. I thought of the case this morning and I haven't had a chance to look through all the details, but I will do that and sit down with you on it.
Okay.
But to kind of explain. Well, let me talk about this picture, and it will lead a little bit to what that concern was. So this is actually what's going on inside the deferred allocator, the deferred allocation stuff. So I talked before about the underlying allocator, right, which is the thing that manages ranges on a heap. And I have three of them here. The most obvious one here is the current allocator, which is basically the current state of the heap. And so in this case here, I've got an instance 1, instance 2 that are currently, from the data plane's perspective, currently living in the heap. And then I have two lists of pending operations. One is a list of pending releases. And even though it's called pending releases, it turns out there's a situation where it also includes ready releases. And I'll describe that in a moment. And then I have a separate list, which is pending allocs. And in the code, these are written as two different lists because they store different things in them. But the picture here is done on purpose. Conceptually, they form one list where releases and allocs have a total order over all of them that is important for the allocation state. And in particular, each pending alloc remembers what the newest pending release was when it showed up. So these two allocations for I3 and I4 showed up after I2 was scheduled to be released, but before I3 was scheduled to be released. And that is very important when we go try to actually complete deferred allocations. So I have these lists in the order they came, and so releases basically just know which instance is being released and what the precondition, what the unsatisfied precondition is. And so if you're here, I1, I mark this one as actually already being complete. And then allocations, they know which instance ID is being allocated. Again, we assign that ID eagerly. They know how much space they need, and they also have an event associated for their created post condition. And so whereas this is an input event, ePost is basically an output event from this. And so based on the state of pending releases, based on what's in pending releases and pending allocs, there's another allocator that's maintained, which is called the future allocator. And it basically describes what the heap looks like. By the way, can you guys see the mouse that I'm moving around? I should have asked that before.
Yes. Yeah, we can see.
Okay, good. Yeah. Doesn't help to point to stuff that nobody can see with your finger. Anyway, so if you were to apply all these releases and acquires in this order, releases and allocs in this order, you would see that this is the future heap state, and so that's what future allocator is tracking. And the reason we do it this way is, I can and in some cases must regenerate this from these lists. But for efficiency reasons, it's easier to maintain this. So when I add a new thing onto a list, I don't have to rebuild the whole thing. I just tack the new thing onto the end and modify the future allocator state. Then the one other allocator that shows up is something called the release allocator. And this is similar to the current allocator in that it only holds completed allocations. But it does include the effect of any releases that are ready but are still on the pending list. So in this case, I1 here was ready, and it is removed from the release allocator's state of things, but not from the current allocator because we haven't popped it off the list here, and I'll explain why we can't pop it off the list in a moment. But so when we go look at the basically the contents of the local managed memory, these are the 5 main data structures you'll see. You also see a mutex, which covers all this, I guess. Hopefully the picture sort of makes sense.
So why is I2 on the release allocator? Like if it's on the pending release list?
Because it hasn't been released yet, right? The precondition hasn't been satisfied.
Oh, I see. But I1 is gone because I1 didn't have a precondition, so you could pop it off immediately.
It did, or either didn't
Or
have
satisfied.
a precondition, or it did and was satisfied.
Right, and so that's already gone. So that's like an immediate effect.
That's right.
Okay.
That's right. So, and in particular, and I'll get it out here. I didn't show the effect of it, but seeing, once we pop I1 off here, it might be that we look at it and say, could I3 actually fit in this hole, right? And so this is going to be one situation where, even though we keep these things in order, there's basically rules for basically applying the releases out of order if they actually complete out of order, and possibly be able to do satisfying allocation earlier than it would have otherwise, right? Basically, let me talk about it now, right? So the main reason, a big reason why each allocation is associated with the previous release is that the only way it gets on this list is if the future allocator said there was room for it. And that future allocator takes into account every allocation and release up to that point. And so I know that if the current catches up to this point, then I know this allocation is going to succeed. And so basically, if the releases all happened in the order they were requested, if they all preconditions were all satisfied in the order they were initially requested, then all the allocations could be satisfied in exactly the same order, and it would basically just be a delayed. The thing we played out in the future is just literally a delayed version of what happens, what actually happens. However, if there are cases where releases happen out of order, like this I1 releasing early, then it is possible, but not guaranteed, that we can satisfy some older releases using a newer, older allocations using a newer release. And you can't always do it though. And so the reason why it has to do with fragmentation, but I'll talk about it in more detail.
Right. So releases can happen. Go ahead, Manolis.
I was going to ask, is there any relationship between the order or where these things are placed on these data structures and the events themselves? Like, is there any precondition, post-condition relationship between the pre's and the posts? Like, if something comes after like I3, is it guaranteed to be like a descendant of I2's pre-event or anything like that?
It's not, but it could be. And actually, that's a great question, because that's one of the wrinkles. The reason we associate these allocations with this release is that essentially, as soon as Realm tells Legion about this post condition, then from Realm's perspective, any future event that Legion hands Realm might incorporate that post condition in some sense. So actually, let me pick on I4 instead of I3, because I3 is clearly related. But right, so in particular, it may be that the precondition for deleting I3 is derived in part from the post condition of I4. And Realm doesn't have that visibility. So Realm has to be conservative and assume that basically any new precondition given to it after it has handed out a post condition may be related. And therefore it would be unsound to move I4, to make I4 dependent on this release of I3, right? Because that might create a cycle.
Okay, so this picture doesn't consider the Realm event graph at all, it sounds like.
No, and the and that basically gets back to that conservatism, right? In theory, we could be more aggressive if we could actually look ahead or look backwards, I guess, when I3 comes on. If we can show that I3 isn't derived from I4, right, then maybe it would be okay to put I4 after I3, but we don't currently do that. The other thing is that if we knew that I3 was going to trigger eventually, this is that ballistic idea, that I don't even necessarily need to know that I don't have to walk I3 back directly, as long as I know that I3, this precondition for I3 is based only on things that have already been literally scheduled for execution. Then that's good enough, because this one hasn't been scheduled for execution until it's completed. And so that would be good enough to avoid the cycle. But the conservative thing to do is to make sure that if we ever rejigger this list, we don't ever want to associate an allocation with a release that came chronologically after it into the data structure. And that's the way we avoid deadlock.
There's another side to this also, which is from a user side, it's very bad if you do releases with user events that are not going to trigger, or that might trigger with something like earlier in the allocation list, but you haven't hooked that thing up in the right way. So like, doing just like instance deletions or releases, with user events that are untriggered is very scary.
Yes, although this conservatism limits a lot of the potential damage, right? It's impossible to connect these two up because it's impossible for, actually, let me try to get it right. Anyway, actually, that's a can of worms. So let me leave that alone for now.
Yeah,
but,
that's fine.
You need to be super careful, and
Yeah.
That's actually why the ballistic event thing would solve that. Basically, it would mean if you have a user event that has not been actually requested to be triggered, then it would hold releases for that basically in their own little area that aren't considered until we know if they're actually going to happen.
Yeah. Yep.
But that's for future work.
Okay.
I do want to get to. By the way, I'm not going to walk through all lines of code because, as I said, it's horrible spaghetti. I'm just going to give you a high-level picture. I figured the slides were more important, and so my last couple slides are describing the algorithm overview in 2 slides instead of 2,000 lines of code. So the way to think about it is there's basically 3 operating modes for the deferred allocator. The first one is the simplest, where there aren't any pending allocations or releases. So in this world, the only allocator we care about is the current allocator. And whenever an allocation request comes in, it's great. We test against the current allocator. If it fits, great, that's success. If it doesn't, then it's an immediate fail, right? There is the future is equal to now, and something either fits or doesn't, and we can be authoritative either way. Similarly, a release with no precondition is also applied directly to the current allocator, right? This is basically a blocking heap management mode at this point. The way we fall out of mode number 1 is if you do a release with an unsatisfied precondition, right? So if a release comes along that can't happen now, but will happen later, then we don't modify the current allocator. We stick this release on at the beginning of the pending releases list. And we now clone the future allocator from the current allocator and apply the release just to the future allocator. So, and we'll switch to mode 2. So the way to think about it, right, is that sort of, if on this slide here, if both of these lists were empty, then clearly the future allocator would be identical to the current allocator. And the way the implementation works is we don't even bother maintaining the future allocator until we need to. So we just maintain the current allocator, and only when the first thing goes in one of these lists, do we spawn the future allocator. And the other thing is the first thing is always a release. It is impossible to have a pending alloc before you have a pending release, because if you have an alloc that's not possible now and there's no releases in the future, then it's not possible in the future either. And so that's why we can do the rejections immediately in this case, and only the releases go into the list. So hopefully mode 1 is not too surprising. Mode 2 is when there are pending releases but no pending allocations. And in this case here, if we get an allocation request, we still first test it against the current allocator, right? If we can do, even though there's pending releases, if we don't need those pending releases and we can successfully allocate based on the current state of things, then we go ahead and do that. There is a little bit of fix-up needed for the future allocator because, and by the way, this is where the determinism matters, right? That if determinism says that if I alloc A and free B on the current allocator and the future allocator, I will get the same thing. But it's not true that alloc A and free B may result in a different end state than free B than alloc A. And so in the current allocator, I haven't done either, and I'd be just doing the alloc. But so you won't get the same result if you apply the alloc directly to the future allocator that has the free in it. Instead, you basically have to do the allocation in the current allocator and then rebuild the future allocator by reapplying the pending releases. In theory, if you have an allocator that allowed you to allocate at a specific location, then you might be able to fix this up, because basically what you just want to make sure is that both the current and future allocator agree on where B would be allocated. And so if the future allocator knew how to actually say, oh yeah, and put it here, even though that's not where first fit would have said to put it, then that might be slightly improved. So that's the case where it works against the current allocator. If it doesn't work against the current allocator, we're not necessarily out of luck. What we then do is we test against the future allocator. And if the allocation that's been requested works against the future allocator, well, then the pending releases would be sufficient to make this allocation succeed. So we will tentatively accept the allocation, and we'll send that alloc result in the affirmative to Legion, so it can tell the mapper, yes, we think your instance is going to be allocated. And then we will switch to mode 3. Whereas if the allocation can't even succeed against the future allocator, then this is a case where we again can fail immediately, right? Even if all the pending releases we've been told about all happened, this allocation still wouldn't work. Then there's no guarantee it'll ever work, and we fail it right away. And then releases are actually the same as mode 1, right? Since we have no pending allocs, a release with no precondition can be applied directly to the current state, whereas release that has a precondition goes on the list and modifies the future state. So that makes sense to folks? So mode 2, we're maintaining a non-empty list of deferred releases, but no deferred allocations. And so as long as we can still do allocations based on the current state until that runs dry, and then we'll switch to mode 3 where we have both pending releases and pending allocs. And I will do that next. This is where it gets a little bit gnarly. If there are any pending allocations, and quick trivia question, hopefully it's obvious now why there is no mode for pending allocations and no pending releases. That would be a failure of the algorithm, because a pending allocation that has no release to enable it is stuck. So in this case, we have both, and if we have any pending allocations, then every single allocation request always is tested against the future allocator. Basically, newer allocations aren't allowed to jump ahead of older allocations in the queue. And so we test everything against the future allocator, either accepting it in a deferred way or, again, immediately rejecting if the future, even after everything that's in flight is done, would not support the allocation. And then similarly, all releases go into the future allocator, or apply to the future allocator and add depending releases, even the ones that have no precondition. So conceptually, we're going to put them on the list, but then the very next thing we're going to do is trigger the, hey, one of the pending releases is now ready. What do I do about it? Which is the second half of this. And that comes in 2 forms. The easy case is if it's the oldest release that comes ready, well, then the future is becoming the present in the order we expected, and life is simple. Basically, that release and all the allocs that were directly associated with it are all applied to the current allocator and completed successfully. And because of the determinism, we know that all those allocations are going to succeed, right? That basically we're applying the operations to the current allocator in exactly the order they were applied to the future allocator, and therefore they're guaranteed by the algorithm to succeed. And that's pretty simple. And you don't even have to go past the first release, because you know that the next one will definitely fail because it failed the first time. It failed the previous time. The trickier case is if a newer release becomes ready. Then this is where the release allocator kicks in. So we now clone the release allocator from the current allocator and apply the ready release. And now we look at the oldest allocation and ask, would it work on this release allocator? So basically, if we did the releases out of order, would it make some of the allocations now successful? If so, then what we're going to do is we're going to tentatively apply them. But once we do that, now we have to basically make sure the future is still possible. And so what that means is the release allocator becomes the tentative current one, right, showing the ready release and the allocations that seem to work on the current state. And then from that, we build a tentative future allocator, which reapplies all the releases and remaining releases and acquires that are pending in the order they were requested. And if that works, then great. We allow the allocations and swap in these tentative ones for the real ones. But it's actually it's quite possible that an attempt to replay all the pending releases and acquired allocations on this tentative state will fail. And the reason is that by doing the releases in a different order, then the allocations might end up in different places, and fragmentation-related issues may cause an allocation that would have succeeded before to fail now. And we never want releases completing successfully but out of order to cause an allocation that we said would work to not work. So in that case there, if we run into that situation, we basically unwind it. We don't release we don't do the release out of order. We just let it sit in the queue, even though we know it's free. And the reason is that it would be too expensive to go try to figure out what is the right, what is the set of allocations that can be granted without causing other ones to fail. If we were to find a situation where that conservatism was hurting us, then in theory there's a space to play around in there. It's pretty nasty to make sure you get everything right, but effectively coming back to this picture here, right? If you can come up with any reordering, we said that I can never move an acquire. I can never make an acquire depend on a later release. But it's okay to make a later release move forward without changing the dependencies. And if I can do that, then and show that I can still build a consistent future allocator that has all the pending releases and all the pending allocs applied in the new order, then I've got a plan, and I can now take anything that's ready off the front and apply it. And if I can't, then the conservative thing is just to do things in plan to keep doing things in exactly the order that seemed to work before. That makes sense? Sort of?
Got a question. Apologies. So how expensive it is, if to put it this way, if to rebuilding a future allocator?
Well, and this gets, so the answer is it depends on the underlying allocator. And this is why I said it's important that the basic range allocator is a pretty cheap one, right? Is that, if there are end things in this list and we decide we want to pull the thing from the end to the front, then we are going to have to replay and allocations and releases on an allocator. And you want that to be relatively cheap. So that's part of the reason why I went with first fit, right? First fit is constant, is not quite constant time, but tends not to walk lists very much to find available spaces. For releases, we do maintain a map that maps from a instance handle directly to the range that it fits. So there's a login lookup there, but then we have the double linked list, so it's free. It's constant time to find the stuff around it. So you can build pathological cases where it is very expensive, and therefore you could also imagine cases where a heuristic kicks in and says, actually, no, the list of pending releases and acquires Alex is too long. I'm not going to try to reorder things just because I think it would be too expensive to try to rebuild that state. Right? If you apply releases and Alex in the order they originally applied, then you don't waste any effort. Right, the future allocator, basically the current allocator basically just converges to the future allocator. I guess you did things twice instead of n times, but only twice. Mm-hmm. It's only when you reorder things that it can get expensive.
Okay, thank you.
Okay. And then the last thing I want to talk about in the slide, rather than trying to point at code, gets to cancellation. So everything I talked about here is cases where every alloc and release that Legion told Realm was going to do does actually happen. And the only poisoning happens when, for instances that can't possibly be allocated based on the future allocator state, and Realm immediately poisons the event and returns it to Legion. There are other things that can cause things to be poisoned, like predication or other failures, and those interact with the allocator as described here. So allocations are actually pretty simple because an allocation basically sits in this limbo here until its precondition is satisfied. If it turns out the precondition is poisoned again, we just forget about it. We haven't put it in the data structure yet. It hasn't hurt anything, and so that's actually not too bad. The real challenge is when a release has a precondition that's canceled or poisoned. And basically what that amounts to is, looking at this picture here, it basically amounts to one of these releases goes away, just completely. It just vanishes from the list. What that means is that the future allocator we built and possibly allocations were based on that. We need to go basically rebuild it and make sure it still works. And so what this is the other case where we rebuild the future allocator. So basically we wind it back to the current allocator, and we just reapply allocs and frees in the order that, in exactly that total order that they were originally applied, skipping the one that was canceled, of course. And now it's possible that once you skip over the one that was canceled, it's possible that allocations start failing, right? Because they may have depended on that particular release. And if they fail, we poison those and cancel those too and remove them from the list. So basically, it's just a filtering pass of remove the release that was canceled and remove any allocations that cannot be applied in their original order and mark those as failed as well. And whatever's left becomes the new future allocator state. So it's basically a one sort of a order n rewriting of history when a cancellation occurs. Obviously, the fact that this can ripple into other allocations can mean that you should be really careful about canceling a release because you won't know what other allocations, what other work that you've been able to describe to Realm based on the assumption that allocation was going to succeed. But if you need to do it, you need to do it. Okay, I've used nearly the whole hour, so let me spend 5 minutes kind of pointing at lines of code real quick, and folks that are interested can dig into it and ask me questions, or if people want to do another round 2 of this with the more gory walkthrough of the code, we can consider that. But the basic, actually, I need to switch sharing here real quick. Let's do that, and then let's do this is the right one. Hopefully people can see GitLab window.
Yep.
So instance allocation and destruction goes through inst-impl because they're methods on a region instance, but those pretty much all the allocator stuff actually happens in the memory implementation. So that's memimpl.h.inl.cc. So in memimpl.h, the main things to look for are there's a memory impl which supports all the general memory interface and has hooks for deferral allocation, but doesn't actually implement it. The implementation of the algorithm I talked about is down in this thing called local managed memory. And then the allocator I talked about, the basic range allocator, is right here. And so you see it has, as you might expect, it keeps ranges based on the range type. There's the doubly linked list. This is the lookup that lets us do login deletion of ranges. And then the basic methods we have are adding a range. Basically says you can start managing a range. So this allocator can actually manage disjoint ranges if you allocate things in pieces from an underlying allocator. But then once you've done that, it's got can allocate, allocate, deallocate, and lookup is the one that says give it a tag, tell me where it actually lives in memory. The main methods that I showed in my timeline, there's allocate storage deferrable and immediate, and release storage deferrable and immediate, and then this attempt deferrable allocation. And then there's an important helper method which comes into when releases are done out of order. This is that method that basically captures the idea of let's see if we can do releases out of order and still build a new consistent future. And if so, here are the allocations that succeeded as a result. All the guts for basic range allocator are here in the inline thing. As you see it, it's relatively simple code. It could be fancy. It absolutely could be fancier. Whether it's the right thing to make it fancier is a question of whether the overhead is worth the cost. And then let's in the C file, we will go find local managed memory. Attempt. So here's attempt deferrable allocation. So let's see. Yeah. So here's the base case. If pending allocations is empty, then can we allocate on the current allocator? Great. If so, just do it. Otherwise, if it doesn't fit, then if there are releases, if there's no releases, right? Well, then we're in mode 1 and we have to fail immediately. If there are releases, then we test against the future allocator. And it actually looks like I don't build it until the first time we actually need it. So it's further laziness. But we build it, and then we test against it. And if it works, then great. We say this is tentatively accepted. Otherwise, we can fail it immediately again. And then down here is the case where if there are pending allocations, right, we just blindly put it on there. We don't even, we test against future allocator, then we stick it on. But we don't ever try to do an immediate allocation for that. Releasing is, again, many more cases. Let's see if I can call out key things, right? If there were no pending allocations, right? So this was the mode 2 case where it's relatively simple just to either apply immediate ones or put it on the list. If there are pending ones, then this is what now we're building the release allocator. We're attempting it, and we're testing against it, and if it works, then we can reorder things. Otherwise, we just stick it back on the list. Because of the way these things take mutexes, there's your mutex. All the actual any allocations and releases that are actually going to happen get queued up and applied outside the mutex so that we don't hold the mutex for very long. Let's see, storage immediate is not super exciting. And then down here is the gnarly one, the release reordering case. So this is the one that basically tries to walk through the list, figure out which things we can reorder, and then try to replay it. And so we're building this test future allocator. And if we got all the way to the end, then great, we swap our test allocator for the current and our test future for the future. And the release allocator is now seen as current allocator. Otherwise, we just unwind it all and say, we'll get to it later. So basically, once a pending allocation goes in the list, the only thing that gets it unstuck is a release coming ready. Either the first release that comes ready, or in some cases, if this test fails, then we know at least one other release is going to happen later, and it will shake things loose. So again, I don't think it would be useful to walk through all the individual lines of code, but folks that want to do it offline and ask me questions are more than welcome to. If enough questions accumulate that we should do another round of conversation about it, I'm happy to do that. But I have successfully chewed up everybody's hour, so I should probably stop talking for now. Take any last quick questions, and thank you for your attention.
We can go a few minutes over too.
Okay, I'm fine with going over if folks want to stick around, yeah.
So can I come back to the CUDA malloc async question now?
Yes.
Do you
right.
wanna...
Okay. Yeah. So how is it different from CUDA malloc async? So one big difference between this and CUDA malloc async is that CUDA malloc async does not allow for basically the non-ballistic release preconditions. Right. When you do when you do a CUDA free async, right, that is treated by CUDA as something that is absolutely definitely going to happen. Right. There's no way to say just kidding, it's not going to happen, or it's not going to happen until later, unless you want to deadlock it, CUDA. It basically, it doesn't need to maintain the current state. It knows there's only a future state because it can always put things after that future state, which, as I understand it, is when you do a CUDA malloc async, it's not maintaining a current allocator necessarily. It's just looking at the future allocator, and it if it decides it's going to use a release, a free that's already queued up, then it just orders you with the stream that's doing that free. And what that means, though, is that a deferred allocation in CUDA malloc async is irrevocably tied to a given free at the point it's requested. And I say that with reasonable confidence, but not with certainty. So if somebody like Corey wants to come in and tell me that I'm wrong, this would be a great time to do that. Like I said, I don't think I'm wrong. I think basically it's using it. So whereas in my model, we have the ability to reorder releases. I don't believe that CUDA malloc async, and I'm pointing at slides that you guys can't see right now. Sorry about that. I won't bother with this. But basically, I don't believe that CUDA malloc async is able to reorder the way that the realm deferred allocator is.
I don't think it is either.
Right. And in the stream-based model, maybe you don't need to, because it's just about CUDA uses streams, but it still has a fairly solid notion of what logical order things are happening in, whereas Realm wants to handle things possibly wildly out of order. Just because a given release was asked for much later than another one doesn't mean it's going to happen much later than another one, whereas streams are kind of FIFO-ish in that nature.
I was going to also say the memory pool is actually coupled to the stream too, right? And so if you have multiple streams, you kind of fragment your memory space, whereas Realm 1 doesn't have that problem.
That sounds right, yeah. I did briefly touch on how to write that add range method on the thing. Sorry, let me arrange my thoughts. It is currently the case that everything that does deferred allocation uses a straight up, sub-allocation model of get one big pool of memory and then manage it with this range allocator. The reason that add range method that is there is to allow for cases where the underlying pool of memory is also grown over time. And so I don't have a mode for that right now, but you could have a case where if an allocation fails, you might go try to allocate more memory from the underlying system and add another range to the allocator. And if we did that, then that I think would just fit because we're not asking the underlying OS allocator or CUDA malloc or whatever to understand these future and current and release states. Then adding new range would be the sort of thing that's done automatic, instantly to all the allocators. Although having said that, no, you couldn't do that. You'd have to apply to the current allocator and then rebuild the future allocator exactly because of the
Yeah, I think the lack of fragmentation of the heap into smaller heaps is actually important. Like there's no, like in the CUDA world, you have to split, CUDA malloc from CUDA malloc async on the individual streams, and each of those are separate pools. And here you just have one heap, right? That's managed through the same API for everything.
Well, and that means all the realm stuff gets to use one heap, but it still has to take it away from.
Sure.
It still takes it away from say the CUDA malloc async pool.
Yeah.
But yeah, we don't have time.
There's also a central allocator, right? Since it's one pool for every quote unquote stream of realm events, right? There's no, like, the stream model is, I guess, trying to be independent, completely independent as a submission of work, right? Whereas you have a central place and you're making up.
That's right, and that's consistent with the general thing, right? That whereas CUDA has FIFOs of tasks with the occasional edges between them, right? What Realm has is just one big flat operation graph, and so it's kind of that same globalness applied to the allocator as to the operation graph.
Mm.
Any other questions?
Is there any notion of fixed blocks of memory? I mean, are the cells multiple of fixed blocks or whatever?
Yeah. Really, when I said size here, it turns out that each allocation has both a size and an alignment constraint. So the range allocator thinks in terms of bytes, but we honor whatever alignments each individual block asks for. And so that's yet another way you can get fragmentation. And because of the determinism of the allocator, we can cope with that. Right? That doing allocations in two different orders with different alignments might cause a very different result, but as long as we do them in the same order both times, then we know that we'll get the same good or bad fragmentation.
But just to shed some light on CUDA malloc async, like, it is true that if you have two different streams and they never synchronize with each other, they can't share each other's memory. But that's mainly because there's no logical ordering between them. If you use an event in between them or whatever, the CUDA driver would be able to use the memory. So
that's right. Once you've forced an ordering between them, then it knows that that any acquire in the second stream will be ordered after the freeze in the first stream, and therefore they're fair game.
Right. Yeah. But and also there's some opportunistic detection as well. Which you can enable.
Okay.
Yeah. So it is fair to say that there is often in practice fragmentation, but that's because the tasks kind of run with no defined order, right? And I don't say there's theoretically unnecessary fragmentation.
Okay. So actually, kind of another way of asking that question is: Does CUDA malloc async ever create edges between two streams? Right. If I want to do a malloc async in one stream and I don't have enough memory there, will it go look for another stream that has some freeze and add an edge between those streams, or will it always go back to the global pool?
That's a good question. So essentially, I think by default it doesn't create edges. I don't know if we added a mode where it would, but certainly by default it doesn't. But also what it can do kind of in between is opportunistically steal from another another stream if it so happens to have already like landed the free.
If the free has already happened. And
Yeah.
so conceptually that's sort of similar to my release allocator, right? If you see a free that's already happened and it works for you and you can show that it doesn't mess anything else up, then you can grab it.
Right, but you can disable that for better reproducibility. So that's a fair point.
That makes sense. And so what I want to say is, the same kind of underlying thought process that causes CUDA allocation to not want to put edges, not want to create edges between streams, is the reason that this allocator doesn't want to wants to be able to reorder releases, right? You don't want to put an edge in because you don't know that that's the right ordering, right? If you add an edge in and it turns out the first stream was really slow, then you delayed the second stream for no good reason. And if some other edge was a better one to add,
exactly,
then you want to be able to do it based on when frees actually occur. And so right, the way this algorithm does that is it tentatively knows where it's going to get it from. And that's what the future allocator is describing. It's saying, I have a plan that says I can satisfy all these allocations if they come from specific places. But we have the ability to tear that up and make a new plan that also satisfies all the allocations if it turns out that another such plan exists.
Yeah, no, that makes sense. Just wanted to, just wanted to make sure the CUDA allocation algorithm was clear.
Yeah, no, that's good, and I think they're pushing on things in slightly different ways, and so it's totally reasonable to ask, could CUDA pick up some of these ideas, or conversely, should Realm go pick up some of those ideas? Right now, I think the centralized allocator is sort of a bottleneck from an allocation point of view. But as I was saying before, we haven't actually seen any cases of that, I think, where the throughput of managing the deferred allocation state is problematic. I guess Art asked earlier, you could build a pathological case, but nobody has so far in practice.
Right.
Good enough for today?
There's no more questions. We'll be back next week for Legion Week, and then Sean, you'll be back in 2 weeks for more Realm stuff.
Yep, sounds like a plan. And everybody knows how to find me if you come up with questions later, or if you look at the code and decide it's terrible and want to fix it, then let me know, and I will say yes, please do.
Okay, thanks everyone.
Bye now.